Hello students, my name is Shashank and we are doing a crash course on chemistry of 45 days for the upcoming JEE exam. And today I will be teaching the chapter which is thermochemistry. So thermochemistry is an important part of thermodynamics. So thermochemistry, we will mainly deal with the thermochemical equations and try use it to find the enthalpy of different reactions. So first of all, we will start with the Hess's law of constant summation. So what is Hess's law of constant summation? It says that we can find the enthalpy change of any chemical reaction by using the initial and the final state, which means we do not need to know what is happened in the pathway or in the you can say in the way between carrying out that reaction. We have to only ensure what is the enthalpy change accompanying the initial and the final state. And using this law, we can find enthalpy of reaction for many equations. Okay, so why is it so? We already know that delta H or enthalpy change, delta H or enthalpy change is a state function. State function. Yes, we know it very well. So it is a direct outcome of this thought process that yes, since it is a state function, so it will be only dependent on the initial and final state. And this Hess's law will be very useful. So we will use the normal algebraic, you can say algebraic summation to find the enthalpy change for various reaction, such that we can use it for the you can say that for suppose we are carrying a reaction from A to B when B to C, then we can directly find from A to C by adding all those reactions. So let us see it how. Suppose consider we have a reaction that is happening like A plus B is giving C plus D. Now the reaction goes through four steps. The first is the reaction goes from A to X plus Y. Then the B reacts with X and give us Z. Then this Y which is formed gives us C, and the Z which is formed gives us D. So these are the four steps. It happens in four steps having different enthalpy change, that is delta H1, delta H2, delta H3 and delta H4. Now suppose we have to find the enthalpy change accompanying this reaction, that is A plus B gives C plus D. Now if we add all these four reactions like this, suppose we are adding these four reactions, so we will simply do the algebraic sum. So A will come here, A, yeah, then we have X. So this X is on the right side and this X is on the left side, so they both will get cancelled. Similarly this Y and Y will get cancelled. Let me denote it with a different pen. Yeah, so this X and X gets cancelled, so because they are on the opposite side of equation. Similarly this Y and Y and this Z and Z. And what the reaction that we will get? What is the reaction that we will get? So we will get as A and B are on the left side, A plus B, and the reaction we will finally get is C plus D. So this is our desired equation as well. Yeah, so you can see here that we are simply using the algebraic sum and finding the delta H. So how we are finding the delta H is that one thing to keep in mind here is that these are called the thermochemical equations. So all these four equations are called thermochemical equations. So they give out the information about the reaction, that how much is the enthalpy change and what are the reactants that are taking part in it. So such kind of equation is called a thermochemical equation. Plus these are giving the qualitative quantitative analysis also, that how much moles of B is reacting with how much moles of X to give Z. So all this kind of information is given by this so-called thermochemical equation. Now if you have to find the overall enthalpy change for this reaction, that is A plus B plus C plus D, then how we will find it out? So since we have added these four equations normally in the algebraic sum, so their enthalpy change will also be the same, that is delta H1 plus delta H2 plus delta H3 and delta H4. So this is the thing here. Now, now we'll see various enthalpy of various reactions. So earlier we have seen that we have reactions and comparing them we have enthalpy change. So this reaction have different enthalpies. So different type of reactions like sublimation reaction or vaporization reaction, atomization reactions. They have different kind of enthalpy. So we will see them one by one. So the first one we have here is called as the bond dissociation enthalpy. So the important thing in while reading this enthalpies is that you must know the definition very well. Means if every statement and every word is very important here. So what is bond enthalpy? So bond enthalpy, dissociation enthalpy is something that it is the enthalpy change associated with the breaking of particular bond, and it is calculated for 1 mole. It is calculated for 1 mole. So this important point should be mentioned here. So the enthalpy change associated with breaking of 1 mole. It is 1 mole here. So this example will make it clear. So you can see here that we are taking 1 mole of this hydrogen. Yeah, and we are breaking this bond between H and H. So this is the HH bond, and we are breaking this bond to get 2 molecules of hydrogen. Yeah, it is very clear. So in this way, you can find this bond dissociation enthalpy, and this enthalpy change accompanying this reaction is called the bond dissociation enthalpy. So for this reaction, it is given as 436 kilojoule per mole. Now, this was for the diatomic molecule because H and H are there are two atoms present there, so it is a diatomic molecule. Now suppose we have a polyatomic molecule like CH4. Now CH4 has 4 CH wedge bond like this. So suppose this is CH4, so it will have 1 CH, 2H, 3H and 4H. Now it will be broken in in three steps, four steps you can say. So first this bond, then this bond, then this bond and this bond. Now you can see here that we have suppose I have numbering this all. So this is suppose H1, H2, H3 and H4. Then we calculate the bond dissociation enthalpy for each of them. So it will be simply delta bond H1 is for this H1. Now we have for different one, that is bond H2, bond H3 and bond H4. Okay, the same thing written here also. So we are doing it in four steps, that are CH4 is going to CH3 plus 1H is given out, that is one CH bond is broken. This much amount of energy is released. Then again we have the CH3 molecule. This has again one hydrogen, it is broken in second step, and this much amount of energy is released for this one, and we can find that yeah, this is completely broken now. Now you will see one thing here, that we have more than one CH, more than one CH bond enthalpies. So what you will do in this type of in this case, so we will find out the mean bond enthalpy. So for each step we see that some amount of energy is released. So this 427, 439, 452 and 347. Now what we will do is we will simply take the average of all of this. You know how to take average. So we will add all this 4 and divide it by 4 to get the average bond enthalpy or the mean bond enthalpy you can say. And this is the used one or the significant one here. So in this case, in this way you can find it for polyatomic molecule. And for diatomic it is very easy. So we have to break only one bond. So that will be the answer there. We will use this example later on also. So let me, if you add this thermochemical equation simply, so what you will get, so this is another kind of enthalpy of reaction. Now, if you will add this algebraic simple algebraic expression like, So this CH3 and CH3 will get cancelled out. Again, this CH2, CH2 will get cancelled out. This CH and CH will get cancelled out. And what we will get is that CH4 gaseous plus 4 H gaseous plus 1 C gaseous. And we know the summation of all of those, which is 1665 kilojoule per mole. So you will learn this kind of enthalpy in the coming slide. So is a good example. So I'm mentioning it here also. So you can see here clearly that this CH4 molecule is here, methane molecule, is broken into its atoms. Okay, and that atoms are in the gaseous states. So 4H plus C. So this kind of you can say decomposition of this methane molecule into its constituents atoms that are in the gaseous state as well is called enthalpy of atomization. And we'll simply add this 4 and we'll get the answer. So you will see this enthalpy of atomization later on also. Now let us move to enthalpy of combustion. So what is enthalpy of combustion? So enthalpy of combustion is the enthalpy change when we burn 1 mole of something. So we can have a reaction like in the you can say combustion of methane molecule. You can have combustion of any organic molecule, and you have to use 1 mole. So the important point to notice here is that we have to use 1 mole of that substance. So we are burning here only 1 mole of that substance. And whatever the result we will get, so suppose we are burning carbon in the presence of oxygen to get CO2. So here we are burning 1 mole of this carbon, and the enthalpy change accompanying this burning of 1 mole of carbon is called as the enthalpy of combustion or combustion enthalpy here. So for this it is minus 394 kilojoule. Okay. Now we will move to a instrument here that is called as calorimeter. So what is this calorimeter mainly used for? So it is mainly used to calculate the heat exchange, or you can say the enthalpy exchange or the internal energy exchange. Means using this one instrument we can calculate the enthalpy change also, the internal energy also, and the heat transferred also. So how we will do it, we will see it now. So before moving to that, let us elaborate with this structure that is given here. So suppose we are doing our reaction here, and now some kind of energy is released from this, or heat is released from this reaction, and we are keeping it immersed in a liquid. So this container is immersed in a liquid, and this is stirrer here to maintain the temperature throughout this liquid, and we have thermometer here. What we do is that so this is used for combustion process. So we are combusting something, and we are calculating the heat change that is occurring during this reaction. Now what will happen, this liquid, we will first of all, the important thing is that we should be knowing about the heat capacity of this liquid that we are taking. So suppose we have water, then we have to be aware about its heat capacity. Now we will measure the temperature of this water initially, that is using the thermometer that is calibrated here. Now we will let the reaction happen, and as this reaction will happen, some heat will be released, of course, and this heat will be transferred to this liquid that is present outside. This will gradually increase the temperature of the water or the liquid that is present, and we will now note down the final temperature that we have. So we do have the initial temperature, we do have the final temperature, that is we do have the temperature change. Now we will see how we will use it to find out the different kind of you can say the enthalpy change or the internal energy, the different kind of parameters. So let us take we have two types of calorimeter. So basically, those who have studied about it, the first one is bomb calorimetry. So it is a very easy topic to study, so it gives you number very easily if you know simply the formula. So what is bomb calorimetry? So bomb calorimetry is something which has constant volume throughout the reaction. So we are keeping the volume constant here, and then carrying out the reaction, and then we are calculating the temperature change. And I have told you earlier as well that we have to know the heat capacity of that liquid. Now we have the delta T, and we know the CV as we are conducting it at the constant volume, so we will call it as CV. Now how we calculate delta U? So we know the formula, it's very easy. So it is simply delta U is equals to QV is equals to NCV dt or delta T. So this is a simple formula. So we know delta V, we know CV, and since we are only carrying out the reaction, we must be aware about how much substance we are taking. So in this way, if we know N, CV and dt, we can calculate delta U. And delta U is equals to QV, we know it very well because we know that delta U is equals to work plus heat. That is, you can say from first law of thermodynamics. But since the volume is constant here, so the work done will be zero. So ultimately, we will get internal energy equal to the heat exchange. Now next we have the delta H measurement. So what is this delta H? So how we'll measure it? So we know that for delta H, if you have to calculate this using this delta T, then we have to keep the pressure constant, and then we can calculate this delta H. So what is the difference between these two? So in bomb calorimeter we keep the volume constant, and for delta H determination we use this pressure constant. Then we know the number of moles, means the amount of substance that we are taking. Then we know the temperature change, and we simply calculate delta H. And here also we know it very well that delta H is equals to QP, because delta H is equals to delta U plus plus delta PV. Now since delta U is equals to, we know, let me do it. So those who are not aware about it, delta H is equals to delta U plus P delta V. Sorry, delta PV as a whole. Now since pressure is constant, so delta U is equals to P delta V. And we know very well that delta U is equals to delta Q plus delta W, and delta W not, sorry, Q plus W. So delta is used for we can state function, so we cannot use it here. So Q plus W, and W is minus P dV, minus P or delta V. So plus delta V and minus delta V is cancelled out, and we get our Q, or you can say QP, since pressure is constant, and QP is equals to Cp dt. So in this way we can calculate the enthalpy change, the internal energy change, and of course your heat exchange using a bomb calorimeter or a calorimeter. Now let us move to another uh, enthalpy of reaction, which is standard enthalpy of formation. So what does it say? So it is the enthalpy change that accompanies for the formation of 1 mole of a substance using the elements which are in the standard state. So this thing is important here, that the reaction that we are considering, what means the formation of 1 mole of substance that we are considering, it should be formed from the elements which are in the standard state. So you will come to know what is standard states once I make you understand it. So this is the thing. Suppose we are forming CO2 gas. We are finding this enthalpy of formation from CO2 gas. So we are taking the carbon as solid. Okay, and then we are taking oxygen in gaseous phase, and then we are calculating this delta HR. So what do you mean by standard state here? So what this standard state simply means is that we take that state of that element which is stable at standard condition. So the standard condition you know very well. So it is 1 atm pressure, 273 Kelvin. So this is pressure, this is temperature. So these are the standard states. So at this condition, what is the elemental state of that element that you're considering will take only that state. So it is different for different. So you can refer to net also. So some peculiar examples are which is not in the simpler way. So you shouldn't often get caught in that. Is that the first one is bromine. So all the means halogen gases like fluorine, neon, sorry, fluorine, chlorine, these are taken gaseous state, or the iodine also. But this bromine is taken in liquid. Why? We know it very well that bromine is the only bromine is formed in liquid form. Okay. Similarly, for mercury also we take the liquid one. Yeah, so this is the peculiar. So you can look for the standard states in different book. It is given for different elements. So you must be aware about it. That what is the standard state for some common elements at least. So which are all very used in the equations. Now here is a list of the standard enthalpy of formation of some compound. So which is for, you can see here. I have just put it for the reference case. So for chlorine, it is for hydrogen, for size 4. So if you want, you can take a look at it. So why I'm showing you this, because standard enthalpy of formation is very important for knowing the stability of all the compound that we know. So if you take a look at here, so if the enthalpy of formation is positive, that is energy is given out using during a formation of substance, then it will be more and more stable. So for that reason, I'm showing you this table. Okay. Now I have mentioned this atomization enthalpy earlier. So when we have used that methane gas and we have dissociated its hydrogen bond, means cleaved this hydrogen bond one by one, and we got four of this enthalpy. Then we add up and found that we can convert this CH4 molecule that is in gaseous state into one carbon gaseous molecule plus four hydrogen gaseous molecule, and the energy change was 1665 kilojoule per mole. So here, what we are doing is that completely decomposing that molecule or that compound into its atoms which are in the gaseous state. So here's another example. So you can see here. So suppose we have written enthalpy of formation. So do not consider it as, suppose we are taking example here, CH4 gaseous, and we are converting it into CS solid and 4H gas. Then the enthalpy change that is accompanying this reaction is never the enthalpy of atomization. Why? Because we have to convert it into gaseous state. So this is the most important point, is that so we are converting 1 mole of a gaseous atom, and of course gaseous atoms, into into its gaseous states, elemental form. Okay. So this is the in atomization enthalpy. Now next we have the phase transition. So what is the enthalpy change that accompany during phase transition? So we have various phase transitions like from liquid to gas, gas to solid, solid to liquid, and we call it by different names. We'll see them one by one. So here is an example. We are converting liquid into gas. That means we are doing vaporization. So the enthalpy change accompanying it will be standard enthalpy of vaporization, that is delta vap H. Similarly, if we are converting from solid to gas, that is we are doing sublimation, then we call it delta sub H, that is enthalpy of sublimation. Next we have solid to liquid, that is we are converting solid into liquid, so it will be fusion. So it is delta H fusion. So these are the various kind of phase transition enthalpy involvement. Okay. Now we'll move to hydration enthalpy. So what is hydration enthalpy? So whenever we are dissolving something like you can say an ion in a gaseous state into water and making it into aqueous state, then the enthalpy change accompanying that will be called as the hydration enthalpy. So how is it for example? Let us take an example here. So suppose we have sodium chloride molecule, and we dissociate it into sodium plus iron. Okay, and not only iron, you can say gaseous ion, and then we further dissolve that gaseous ion into liquid or water, and then we got the aqueous state of it. Then for that case, so where the conversion takes from the gaseous ion of sodium plus molecule to aqueous ion of sodium plus molecule, then it is called as hydration enthalpy. So here is the example. So we are converting the sodium plus gaseous ion into sodium plus aqueous ion using, and then enthalpy change is accompanying that reaction is called del H hydration, which is minus 406 kilojoule per mole. So during this reaction, you can see that energy is released. Why is it so? Because when we dissolve this kind of ion into water, this ion get stabilized due to the polar interaction of the water molecules uh, behind the sodium plus ion, that is dipole interaction with the sodium plus ion. Now we have the ionization enthalpy. So what is ionization enthalpy? So when we will come to know that ionization in the later chapter when we're in the periodicity. So what is ionization reaction is that we take an electron from an element that is already in the gas state, yeah, and we take 1 mole of that gaseous atom and convert it into a positive ion or a corresponding ion that we get after removing one electron. Suppose you again the example of sodium here. So we are removing one electron from this sodium gaseous atom and getting our sodium plus ion. And the enthalpy change accompanying it is called as the ionization enthalpy, that is 496 kilojoule per mole. Now next we have the solution enthalpy. So it is, as the name says, it is very simple. So it is nothing but when it is the enthalpy change associated when 1 mole of a solute is dissolved in specified amount of solvent. So here the thing that is to notice, that is to keep in mind that we are dissolving only 1 mole of solid. Okay, it is defined, but the amount of solvent that we are taking is will be defined according to the question or the text that we are reading. So it is specified amount of solvent, means it is defined by the user or the uh, according to the requirement we modified the amount of that solvent. So suppose we take a very simple example here. We're taking a sodium chlorides in solid form, and we're dissolving it in water. So we are getting a sodium plus aqueous ion, okay, and a chloride minus aqueous ion. And the enthalpy change accompanying it is called as the delta H sol, or the delta enthalpy, or the enthalpy change of solution, which is 3.9 kilojoule per mole for sodium chloride ion. Okay. Now let us move to lattice enthalpy. So what is lattice enthalpy? So lattice enthalpy is nothing but it is the enthalpy change when 1 mole of some solid crystal which is present, which is transfer, you can say, made of ions, is converted into its ionic form, and that ionic ions should be in the gaseous state. So here's the example. So we are taking the sodium chloride example of solid which is present solid, and we are converting its ion into Na plus gaseous and chloride minus gaseous. So the main points here to keep in mind is that what is the state that we are taking during the reaction change. So you can see very clearly. So suppose a question is given and you are told that okay, take the delta H lattice as this. So you do have to specify earlier only that yes, that we're taking this gaseous state of that sodium plus ion. You cannot convert this sodium chloride into sodium plus solid, or aqueous plus chloride aqueous. So it will be not called as lattice enthalpy. Okay, rather it will be called as this solution enthalpy. Got the point? Good evening, green eyes. Now let us move to enthalpy of reaction. So I have not introduced the enthalpy of reaction in the earlier case because now we'll get it how we will use this different kind of enthalpies and get our enthalpy of reaction. So the reaction will be given and we will add this different kind of enthalpy of reaction accordingly and get our desired thermochemical equation. So suppose we are taking the reaction, that is small a into a, that is a is the coefficient here, small b is the coefficient here, small c, small d, and we are doing the reaction a plus b, which gives us c plus d. Now how will calculate this enthalpy of reaction for this equation? So if you want a general perspective, you can do it simply if you know the standard enthalpy of formation for all of this. So how we will calculate using that? So suppose you have to find the enthalpy change for this reaction. So suppose this is this delta H formation of this C. Okay. So we will multiply this delta H of formation of C with small c with the coefficient that we have. Similarly, we will multiply this delta formation of D with small d, that the coefficient do we have. That is for the product. So this overall, this is for the product. and we will subtract it with the reactant. Now the important thing to keep in mind here is that we have to multiply the delta H formation with the coefficient as well to get our desired equation or a desired enthalpy change of reaction. So this is the important point here. Okay. So suppose we have the standard enthalpy of reaction in place of enthalpy of reaction. So what will be the case for that? So in that case, all the reactant should be in the standard state rather than any random state. Okay, so this should be kept in mind. So if you are told that standard enthalpy of reaction, then we have to take the reactants in the standard states. Now we'll see these examples one by one. So we have different questions. So I will put you 10 questions here, and out of those 10, we have five. I will make give the solution, and remaining five you have to do it by your own. So let us start. So which of this reaction defines delta H naught formation? So here it is asked that which of this equation is correct for delta H naught formation. So we know the definition of delta H naught formation. First is that it should be forming only one mole of that compound, and second is that the initial or the reactant should be in the standard state. So we'll look at it one by one. So here is the thing. So we take the carbon of diamond and O2 gaseous to give CO2 gaseous. So why is this equation wrong? So it is completely wrong. Why? Because the standard state of carbon is, you can say it is graphite, and here the standard state of and the state is taken as diamond. So this one is wrong. The next one is one more thing here, that one mole is occurring. Okay, this point is right, but this the difficulty with it is this thing. Now next question is we have that we are taking next equation we are forming HF, that is in the gaseous state, and one mole is forming. Okay, we are taking fluorine and hydrogen. Yeah, it is also right, and we are taking it in standard state, that is gas and gases. Okay, so this is the right answer. Now next, it is completely wrong in the starting only. So you can see here we are forming 2 moles of this ammonia, and we know very well that in the standard enthalpy of formation we have to form only 1 mole. So this is also wrong. And what is this last one? So it is also wrong. Why? Because we have to take the elemental form in the standard state, and it is not the elemental form at all, this CO. So suppose in this place of CO we have this carbon in the graphite state. Then how many carbons? So we do need one carbon. Okay, so this is, if this was the equation in place of this, then it would have been right, but since it is not, so it is completely wrong. So this is the correct answer we have. Now let us move to another question. So it says that you have to find the heat of combustion of carbon and carbon monoxide. So it is given, sorry, the heat of combustion of carbon monoxide is given. So C plus O2 is given as CO2. It is in gaseous state, also in gaseous state, solid state, and also the carbon monoxide is given. Okay, so the carbon monoxide is also given. And we have to find what is this uh, enthalpy of formation for this carbon monoxide per mole. So we have to find the enthalpy of formation of carbon monoxide. So how we will find it? So let us see. Sorry, I am not aware about the equation, so I take a look at it. Yeah, so we have to find the heat of formation for carbon monoxide. Now let us see how can we form this carbon monoxide. So what are the elements that are present here? It is carbon and oxygen. So it should be formed from carbon, which is a solid state. Then you have to take the oxygen, give the reaction and give it 1 mole. So this is a complete reaction. And what do we have? We have C solid plus O2, which gives us CO2. Okay, which gives us CO. Okay, which gives us CO. So here is the solution. Now we take those, we add it accordingly to get our answer. So we need we need finally this equation. We simply add this, and sorry, we'll simply subtract it, and we get our enthalpy change regarding this equation. Okay, so this is the solution. Next we have, for the complete combustion of ethanol, the amount of heat produced as measured in calorimeter is itna. So we are given the heat that is produced in calorimeter. So since it is a bomb calorimeter, so this delta enthalpy change will be, sorry, the heat change will be the internal energy as well. The amount of heat produced as is assuming ideality of the enthalpy of combustion will be, so we have to find the delta HC. So what is delta HC we have to find. So for that we should know this equation. So we know that delta H is equals to delta U plus delta PV. Now since delta U is known, we do not know delta PV, but if we put PV in place NGRT, so why we are using NGRT? Because this PV equals to nRT is for gaseous molecule, so should the gas, they should be only considered change in number of gaseous molecule only. So this is the formula. Now we'll see the change in number of gaseous molecules. So number of gaseous molecule is 2 minus uh, Ng is equals to delta Ng is equals to 2 minus 3, 2 minus 3, that is minus 1. Okay, so we do have the temperature here, we do have the delta U, we know the gas constant R, it is given here. So we'll convert this gas constant into kilojoule per mole first of all. Kilojoule per mole per Kelvin. We know the delta Ng, so you can use this formula and get your answer. So here's the solution that is also given. So we take this, then we know that is minus 1 R, temperature to 98 Kelvin. So yeah, we have to convert this degree Celsius into Kelvin. So if it is in given in Celsius, have to convert it into Kelvin as well. Now let us move to the fourth question. What is the fourth question? It says that we have the bond dissociation energy of xy, x2 and y2. So bond dissociation energy. So we have to break 1 mole into its gaseous atom. So we have to take only 1 mole. X2 we have 2x gaseous. Then we have y2 we have 2y gaseous. So the ratio is given. So it will be 1x. So delta H bond it is 1x, delta bond H it is 1x again. You can say x simply, and this delta bond H is 0.5x. And the delta H formation for xy is given is minus 200 kilojoule per mole. Means x2 plus y2 is given as xy. So this value is given, it is 200 kilojoule per mole. So this much equations we have, and we have to find the bond dissociation for x2. So we have to find this x value first. So how we'll do it? So we know that this is the thing here, and I've told you the formula earlier that it is, if the enthalpy of reaction is given, then we can simply do it by this thing. So suppose we have to find it, so we can do it like this. Okay, so enthalpy of, let me do it in board. Enthalpy of formation can be written as, so this is a new formula, so I have not told you earlier. So delta H bond summation multiplied by their coefficient, you can say, for product, minus BI, which is for product, BI you can say, for reactant coefficient, summation of bond H reactant. So using this formula, you can simply find out these things. So we have half, we will this put it half of xy, and then subtract it with half of x2 and half of y2, and which will be equals to this minus 200. So it will be half x, and then we will get our simply our answer. The same thing is done here also. X2 half x2 it is, and we got our answer. Okay. Now let us move to our last question that I will solve. From then onwards you will solve these questions. So it is given that the bond of dissolution of BaCl2 and H2 is this much. So we are doing this thing here. And for both it is given kilojoule per mole. And also for BaCl2 of H2O. And we have to find the enthalpy of hydration for this. So how I will do it? So I will show you the solution directly. So this is the thing here. So the two equations are given. Okay. Now for the reaction this much. So we will simply add this both of this two. Okay. And then we will get our answer. Okay. So we will subtract this equation. This last equation will subtract, that is 1 minus 2. And that will be our final answer. Okay. So in this way you can solve this question. Now these are the questions. So I will wait for, you can say, one time. You can pause the your screen and get your answer. So I will give you a way through also if you want. So it is given you have to find the enthalpy of combustion of H2. The enthalpy of combustion of H2 cyclohexane and cyclohexane are given though for all of this. So H2 plus O2, you simply know it what it is. It is water. Cyclohexane, the formula we know that for the combustion of organic molecule. So we will get CO2 plus H2 for both of this, cyclohexane and cyclohexene, both of this. Now you have to find the heat of hydrogenation. So let me give you an idea what is heat of hydrogenation. So it is a new term here. So this is the cyclohexene. So hydrogenated form of cyclohexene is cyclohexene, that is this one. So what is the overall reaction? So we know that C6H12 is for this cyclohexane, so it will be C6H10. That is 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. So C6H10 we have, and we are adding hydrogen to it. And how many hydrogens we need? 2 hydrogens simply to get our C6H12. So this is the final equation you have to get, and out of this much equations are given. So H2 plus O2, which gives us what? H2O, we have. Then we have cyclohexene, that is C6H10 plus O2, which gives us carbon dioxide plus H2O. So you will balance this stoichiometric coefficient. I'm not doing it here. It is n plus 1 by 2, the formula. Then we have the C6H12 plus O2. We have CO2 and H2O again. Now we have this much equations. And the only thing we want is this one. So this is equation 1, equation 2, equation 3. Now we'll put you this all these three equations accordingly and multiply it with the required coefficient. Or you, if and one more thing, if you turn the reaction from right to left, means you can say we are going from here to here. So if you go from here to here, then this sign will get opposite. So if it's negative, we will get positive. And if you are multiplying it with 2, so the whole equation will multiply it by 2, and this enthalpy will be also multiplied by 2. So these are the main peculiarities you have to take care. Then you have to add this equation algebraically, like you do it for x plus y, and get the value of your delta H. Okay, now next is we have the delta H formation for boron molecule, it is given, and delta H formation for fluorine molecule, it is given. We have to find the delta H formation for BF3. So how we'll find it? We know it very well. So what is the delta H formation for fluorine? So for that, the equation, we should know about the equation. It is B2F2 gaseous. And what is this atomization? So it is conversion of this F2 into 2F gaseous, and conversion of this B2 into gaseous. Okay. So I have told you earlier that if you have to find for formation, then you will simply multiply the bond enthalpy with the initial one, and then product minus reactant, and you will get an answer. So in this way you can find for this also. Then next we have is the heat involved in the combustion of methane is given. So this is the heat involved, the combustion of methane, it is given. So how many grams of methane would be required to produce 4451.5 kilojoule of energy? So this equation is for how much? For 1 mole of methane it is given. So for 1 mole of methane, we know that the combustion or the heat of combustion is 890.3 kilojoule per mole. So kilojoule, so 1 mole it is. Of course, it is obvious. So what is the molar mass of methane? So it is carbon, that is 12 plus 4 16. So for it is given for 16 gram of methane. Okay. So for 1 kilojoule, how much it will be? Kilojoule. So for 1 kilojoule it will be 16 by 890.3, and then for 455 you will multiply. So you will use the simply the unitary method to calculate this equation. So you will do it by yourself. So it will help you in polishing this thermochemistry equations. Okay. Now let us move to the standard enthalpy of formation of NH3. So it is given that next question, that is standard enthalpy of formation of NH3 is given this much. If the enthalpy of formation of H2 from its atoms is this much, so we are taking 2H forming H2. So in the gaseous state is minus 436 kilojoule, and that of N2, that is 2N gaseous, is minus 712 kilojoule per mole. Then we have to find the average bond enthalpy of NH. What we have to find is that average bond enthalpy of NH. So here we have HH bond enthalpy, we have NN bond enthalpy, of course, and we know that for NH3 we have to form, then we have to take half of N2, and then we want 3 of H2. So this is the equation. So for this case it is given, it is minus 460. And what do we want? We want it for each NH and get our answer. So let me make one point clear here. So if you find the bond dissociation enthalpy for NH3, so from the formula that we have for the enthalpy of formation, that is product minus reactant, then whatever the bond enthalpy we will get, we will divide it by we will get whatever we will get, we will divide by 3. Okay, and that will be our answer. So you must try it. So if you try it, you will get it for NH3 as a whole. You will get something. So it will be half of this plus half of this, and it will be subtracted from this much, and whatever the value you will get, that will be divided by 3, and then you will get the answer. Now this is the last one. So we have two statements. It is statement and assertion type question. So the enthalpy of formation of H2O is greater than H2O gaseous. Means it says that the energy that is involved in making of H2O liquid is greater than H2O gas, and the enthalpy change of condensation is negative. Means as we are going from H2O gas to H2O liquid, then we are getting a negative sign. So what do we get from here? So I have told you earlier also. So if you are getting a negative sign, which means that it is stabilizing, because it is releasing energy, of course. So this one is the more stable form. Now it is asked that which one is the statement is correct and which is the right explanation for it. So statement 2 is correct. First of all, it is correct because liquid is of course in the more stable state. So statement 2 is correct. Now we have to see that whether statement 1 is the correct explanation of this or not. So if the enthalpy of formation of H2O is more, so you will do it by yourself. I'm not doing it right now because I fall for the trap and give you the right answer. So once you are one step behind your answer. So I'm giving you the hint that okay, so this is the thing here. So if something is more stable, it will give out more energy. Okay. So in this way, you can do this example also. So thank you for your time. So this was all about thermochemistry. So if you want, you can ask questions right now.